Hi everyone, welcome back to this video series on Windows Server 2012, Subnetting a network. If an organization is large and has lots of computers, or if its computers are geographically dispersed, it makes good sense to divide its colossal network into smaller ones connected by routers. These smaller networks are called subnets. The benefits of using subnets are as follows. Reduced network traffic. We all appreciate less traffic of any kind, and so do networks. Without routers, packet traffic could choke the entire network. Most traffic will stay on the local network. Only packets destined for other networks will pass through the router and to another subnet. This traffic reduction also improves overall performance. Simplified management. It's easier to identify and isolate network problems in a group of smaller networks connected together than within one gigantic network. An organization with a single network address comparable to the hotel building mentioned in the sidebar, understanding the benefits of subnetting, can have a subnet address for each individual physical network comparable to a floor in a hotel building. Each subnet is still part of the shared network address, but it also has an additional identifier denoting its individual subnet network number. This identifier is called a subnet address. Subnetting solves several addressing problems. If an organization has several physical networks but only one IP network address, it can handle the situation by creating subnets. Because subnetting allows many physical networks to be grouped together, fewer entries in a routing table are required, notably reducing network overhead. These things combine collectively to yield greatly enhanced network efficiency. The original designers of the Internet Protocol envisaged a small internet with only tens of networks and hundreds of hosts. Their addressing scheme used a network address for each physical network. As you can imagine, this scheme and the unforeseen growth of the internet created a few problems. The following are two examples. Not enough address space. A single network address can be used to refer to multiple physical networks, but an organization can request individual network addresses for each one of its physical networks. If all of these requests were granted, there wouldn't be enough addresses to go around. Gigantic routing tables. If each router on the internet needed to know about every physical network, routing tables would be impossibly huge. There would be an overwhelming amount of administrative overhead to maintain those tables, and the resulting physical overhead on the routers would be massive. CPU cycles, memory, disk space, and so on. Because routers exchange routing information with each other, an additional related consequence is that a terrible overabundance of network traffic will result. Although there's more than one way to approach these problems, the principal solution is that I'll cover in this book, subnetting. As you might guess, subnetting is the process of carving a single IP network into smaller logical subnets. The trick is achieved by subdividing the host portion of an IP address to create a subnet address. The actual subdivision is accomplished through the use of a subnet mask. Although there's more than one way to approach these problems, the principal solution is the one that I'll cover in the book Subnetting. As you might guess, subnetting is the process of carving a single IP network into smaller logical networks. The trick is achieved by subdividing the portion of the IP address to create a subnet address. The actual subdivision is accomplished through the use of a subnet mask. In the following sections, you will see exactly how to calculate and apply subnetting later in this chapter. In the following sections, you will see exactly how to calculate and apply subnetting. implementing subnetting. Before you can implement subnetting, you need to determine your current requirements and plan on how to best implement your subnet scheme. How to determine your subnetting requirements. Follow these guidelines to calculate the requirements of your subnet. 1. Determine the number of required network IDs, one for each subnet and one for each wide area network WAN connection. 2. Determine the number of required host IDs per subnet, one for each TCP IP device, including, for example, computers, network printers, and router interfaces. 3. Based on these two data points, create the following. 1. A subnet mask for your entire network, a unique subnet ID for each physical segment, a range of host IDs for each unique subnet. How to implement subnetting? Subnetting is implemented by assigning a subnet address to each machine on a given physical network. For example, in Figure 8.3, each machine on subnet 1 has a subnet address of 1. The default network portion of an IP address can't be altered without encroaching on another administrative domain's address space unless you are assigned multiple consecutive classful addresses. To maximize the efficient use of the assigned address space, machines on a particular network share the same network address. In Figure 8.3, you can see that all of the Widget Inc. machines have a network address of 130.57. That principle is constant. In subnetting, it's the host address that's manipulated. The network address doesn't change. The subnet address scheme takes a part of the host address and recycles it as a subnet address. Bit positions are stolen from the host address to be used for the subnet identifier. Figure 8.4 shows how an IP address can be given a subnet mask. So you see here the internet router. The router needs only one way of widget. So you've subnet 1, subnet 2, router A, subnet B, subnet 4, and subnet 3, router C. Figure 8.4, network versus host addresses. So class B address, network address 100.001.001.1.001.1.001.1.000.1000. Class B address with a subnet address, network address 100.00.0011.1001. Subnet host address 00000001.0011.1000. Because the Widget Inc. network is a Class B network, the first 2 bytes specify the network address and are shared by all machines on the network, regardless of their particular subnet. Here, every machine's address on the subnet must have a third byte read 00000001. That fourth byte, the host address, is the unique number that identifies the actual host within that subnet. Figure 8.5 illustrates how a network address and a subnet address can be used together. When implementing subnetting, you need some type of hardware installed onto the network. Most of us will just use a router, but if you do want to purchase an expensive router, there is another way. One way you can implement subnetting is by using a Windows Server 2012 R2 machine with multiple NIC adapters configured with routing tables on the server. This type of router is called a multi-homed router. This is an expensive way to set up a router using a Microsoft server, but it may not be the best way. Many companies specialize in routers, and these routers offer many features and more flexibility than a multi-homed router. How to use subnet masks. For the subnet address scheme to work, every machine on the network must know which part of the host address will be used as the network address. This is accomplished by assigning each machine a subnet mask. The network administrator creates a 32-bit subnet mask comprising of ones and zeros. The ones in the subnet mask represent the positions in the IP address that refer to the network and subnet addresses. The zeros represent the position that refers to the host part of the addresses. Figure 8.6 illustrates this combination. In the Widget Inc. example, the first 2 bytes of the subnet mask are ones because Widget's network address is a Class B address formatted as network.network.node.node. The third byte, normally assigned as part of the host address, is now used to represent the subnet address. Hence, those bit positions are represented with ones in the subnet mask. The fourth byte is the only part of the example that represents the host address. So here we go, figure 8.6. Figure 8.6, the subnet mask revealed. Subnet mask code ones, position representing network or subnet address as zeros, positions representing the host address. Subnet mask for Widgets Inc. So 1111111111.0.0.0.0.0.000. So network address positions, subnet positions, host positions. The subnet mask can also be expressed using the decimal equivalents of the binary patterns. The binary pattern of 11111111 is the same as decimal 255. Consequently, the subnet mask in the example can be denoted in 2 ways as shown in figure 8.7. Figure 8.7, different ways to represent the same mask. Subnet mask in binary 11111111.111111.0.000. Subnet mask as decimal 255.255.255.0. The spaces in the above example are only for illustrative purposes. The subnet mask in decimal will actually appear as 255.255.255.0. Not all networks need to have subnets, and therefore they don't need to use custom subnet masks. In this case, they are said to have a default subnet mask. This is basically the same as saying that they don't have any subnets except for one main subnet on which the network is running. Table 8.4 shows the default subnet masks for the different classes of networks. So here we go, table 8.4, default subnet mask, class format, default subnet mask A, network.node.node.node 255.0.0.0, B, network.network.node.node 255.255.0.0, C, network.network.network.node 255.255.255.0. Once the network administrator has created the subnet mask and has assigned it to each machine, the IP software applies the subnet mask to the IP address, to determine its subnet address. The word mask carries the implied meaning of lens in the, or sorry, tens lens in the case. That is, the IP address software looks at its IP address through the use of lens of its subnet mask and to see its subnet address. Figure 8.8 illustrates an IP address being viewed through a subnet mask. Subnet mask code, one's positions representing the network or subnet addresses, zeros, positions representing the host address, positions relating to the subnet address, subnet mask, 111111111111.0000000. IP address of a machine on a subnet 1.130.57.1.56 100000010.0011 1001.0000000001.0011 1000 bits relating to the subnet address. In this example, the IP software learns through the subnet mask instead of being part of the host address. The third byte of its IP address is now going to be used as a subnet address. The IP software then looks in its IP address at the bit positions that correspond to the mask, which are 00000001. The final step is for the subnet bit values to be matched up with the binary numbering convention and converted to decimal. In the widget ink, for example, the binary to decimal conversion is simple, as illustrated in figure 8.9. Figure 8.9, converting a subnet mask to decimal. Binary numbering convention, position value continued, 128 64 32 16 8421. Widget third byte 000000001. Decimal equivalent 0 plus 1 equals 1. Subnet address 1. By using the entire third byte of a class B address at the subnet address, it is easy to set and determine the subnet address. For example, if Widget Inc. wants to have a subnet 6, the third byte of all machines on that subnet will be 0000110. Decimal 6 in binary. Using the entire third byte of a class B network address for the subnet allows for a fair number of available subnet addresses. 1 byte dedicated to the subnet provides 8-bit positions. Each position can be either a 1 or a 0. So the calculation is 2, 8, or 256. Thus, Widget Inc. can have up to 256 total subnetworks, each with up to 254 hosts, although RFC 950 prohibits the use of binary all zeros and all ones as subnet addresses. Today, almost all products actually permit this usage. Microsoft's TCP IP stack allows it, as does the software in most routers, provided you enable this feature, which sometimes is not the case by default. This gives you 2 additional subnets. However, you should not use a subnet of all zeros unless all the software on your router network recognizes this convention. How to calculate the number of subnets. The formula for calculating the maximum number of subnets and the maximum number of hosts per subnet are as follows. 2x number of masked bits in a subnet mask maximum number of subnets, 2x number of unmasked bits in the subnet mask minus 2 equals maximum number of hosts per subnet. In the formulas, masked referred to bit positions of 1 and unmasked refers to bit positions of 0s. The downside to using an entire byte of a node address as your subnet address is that you reduce the possible number of node addresses on each subnet. As explained earlier, without a subnet, a Class B address has 65 534 unique combinations of ones and zeros that can be used for node addresses. The question then is, why would you ever want 65 534 hosts on a single physical network? The trade-off is acceptable to most who ask themselves this question. If you use an entire byte of the node address for a subnet, then why have only 1 byte for the host address, leaving only 254 possible host addresses? If any of your subnets are populated with more than 254 machines, you'll have a problem. To solve it, you would then need to shorten the subnet mask, thereby lengthening the number of host bits and increasing the number of host addresses. This gives you more available host addresses on each subnet. A side effect of this solution is that it shrinks the number of possible subnets. Figure 8.10 shows an example of using a smaller subnet address. A company called Acme Inc. expects to need a maximum of 14 subnets. In this case, Acme does not need to take an entire byte from the host address for the subnet address to get its 14 different subnet addresses. It needs to snatch only 4 bits from the host address. 22.4 equals 16. The host portion of the address has 12 usable bits. Remaining 212 minus 2 equals 94. Each of Acme's 16 subnets could then potentially have a total of 4094 host addresses and 4094 machines on each subnet should be plenty. So figure 8.10, an example of smaller subnet addresses. Acme Inc. network address 132.8 Class B net.net.host.host. Example IP address 0 1 0 dot 0 0 0 0 1 0 0 0 dot 0 0 0 1 0 0 1 0 dot 0 0 1 1 1 1 0 0 decimal 132.8.18.60 subnet mask code. Ones positions representing network or subnet addresses. Zeros position representing the host address. Subnet mask binary 1 1 1 1 1 1 1 1 dot 1 1 1 1 1 1 1 1 dot 1 1 1 1 0 0 0 0 dot 0 0 0 0 dot 0 0 0 0 decimal 255.255.240.0. The decimal 240 is equal to the binary 1 1 1 1 0 0 0 0 dot. Okay, positions relating to the subnet address. Subnet mask 1 1 1 1 1 1 1 dot 1 1 1 1 1 1 1 1 .111.110.0000.0000 IP address of the Acme machine 100.0.000.000.000.000 bits relating to the subnet address, binary to decimal conversions for subnet address, subnet mask 11110000, position value continuous 128.64.32.16.842.1, third byte of IP address 000100010, decimal equivalent 0 plus 16 equals 16. Subnet address for this IP address equals 16. So I'm going to leave it here today for this video. If you like listening, please like, share, and subscribe. Thank you.